Assalamu alaikum wa rahmatullahi wa barakatuh. Today, inshallah, we will start in a new machine, one of the special machines, which is stepper motor. Why we need a stepper motor? What is the difference between stepper motor and other kinds of motors? We are going to describe this in details. So the objectives of our class today is to understand what the stepper motor means, what are the different types of stepper motors, what is the operation of a stepper motor, and how we can control a stepper motor using different control techniques. Firstly, what is the stepper motor as a definition? I will give you an example in order to understand the idea why we need to use stepper motors. Let's assume that we have a printer, and you know the idea of printing. When you would like to print out one line in a paper, you have to stop the motion of the motor in order to print the line. Otherwise, if the motor is rotating and the cartridge is moving on the paper, the line will not be aligned horizontally. It will be moving down. So it will not print it in the right way. So we need to move the motor for instance, for certain angle, and then stop this motor and start moving the cartridge on the top of the paper. Another question, if we moved the motor and stop the motor at a certain angle, and we start moving the cartridge on the paper, the cartridge, when moving on the paper, it's like a torque applied to the machine. So if the machine at a certain angle is stopped working, which means the electrical torque of the machine equals 0 because the machine is not working, this will not allow the machine or the cartridge to print out the line in the proper way because the paper will not be fixed. So we need the motor to fix the machine, which means we need a motor to have holding torque. Holding torque means when the motor is stopped, there is no motion, the load can be catched by the motor. And for instance, if you have three-phase induction motor and you stop the motor operation, you can move the rotor or spin the rotor by your hands. There is no holding torque. However, in this application for printer, we need a motor that can hold the load at standstill. So this is the difference between what we need in this application and the previous motors that we have already discussed. Actually, stepper motor can do that. Stepper motor can work in steps, and also during standstill, the machine hold the load torque, so we can use it in such applications. So it's used a lot in robots, in printers, and a lot of applications we are going to describe in details. But for now, we need to make a definition for the stepper motor based on this, the features of this motor. So stepper motors are electromagnetic incremental device. Incremental, it means it's going to increment the angle in order to move for a complete cycle. This is the meaning of incremental device that convert electric pulses to shaft motion. And here we have rotational motion type. As you can see, it converts electrical pulses, not electrical supply, which means the supply of this motor is not AC or DC. The supply here will be a kind of pulses. So it's a special machine because of that. The motion is special and also the supply is special. Another feature, typical types of stepper motor can rotate at 2 degrees, 2.5 degrees, 5, and so on. So these are the typical degrees required by the motor motion. The rotor position sensor or sensorless feedback-based techniques can be used to regulate the output response. So for this kind of motor, because the motor can move in accurate steps, we can operate the motor and estimate its position without using feedback control. Just open loop control is sufficient to control this motor. So we can define the motor as stepper motor is a digital actuator whose input is in the form of programmed energization of the stator windings, and whose output is in the form of discrete angular rotation. So this is another definition for stepper motor. What are the advantages of a stepper motor compared to different motors? First, the rotation angle of the motor is proportional to the input pulses. So simply, if you know the sequence of pulses which is applied to the machine, you can recognize the motor angle, which angle exactly or which position the motor is working. Also, the motor has full load torque at standstill. This is what means we have holding torque. This because during standstill, the windings of the motor are energized, which means during standstill, the motor is supplied. Precise positioning and reliability of movement, since good stepper motors have an accuracy of 3 to 5 of step, and this error is not cumulative from one step to the next, which means this motor has higher reliability compared to other motors, and this because the accuracy is very or the tolerance of the motion is very small, like 3 to 5% of step. This because we define the switching pulses exactly and we know the position of the motor, and therefore the error is not cumulative. This means if we have error in the first step of the motion and we change the pulse sequences to the next step, we will not have accumulated error. The error can be neglected or removed. And this is considered as an advantage of this type of motors. Excellent response to starting, stopping, and reversing compared to other motors. Very reliable since there are no contact brushes in the motor, as we will describe the construction. No brushes or no commutators used in this motor. So the lifetime of this motor depends only on the bearing of the machine. The motor's response to digital input pulses provides open loop control, making the motor simpler and less costly to control. So because there is no shaft encoder or any device required to make speed control, so this control is cheap compared to other motors, because, for example, in order to control the speed of induction motor, we need to have a speed sensor like shaft encoder, and we have to take the signals of the shaft encoder and use the closed loop control in order to make speed control for the induction machine. However, here for stepper motor, we can operate the machine at open loop control without using any sensor. So the control system of a stepper motor is much cheaper compared to other machines. Also, it's possible to achieve very low speed synchronous rotation with a load that is directly coupled to the shaft. It's easy to apply very low speed because the speed here will depend on the frequency of the applied pulses. Since the frequency is small, the low speed can work properly. Actually, we have a problem with other kind of machines like induction machine. We cannot operate the induction machine at very low speeds. The stability of the machine will not be good. So we prefer this motor in the low speed application compared to other kind of machines. Another advantage is a wide range of rotational speed can be realized as the speed is proportional to the frequency of the input pulses. So the speed here, we can control the motor speed by a wide range. What are the disadvantages of the stepper motor? First, we have a resonance problem, which may occur according to the frequency of the applied pulses and the mechanical motion of the machine. So it can make resonance, and resonance may damage the mechanical parts of the motor. So in design, we have to avoid operating at resonance frequency. Another drawback, it's not easy to operate this machine at extremely high speeds, because the nature of this machine in the operation, it's like operating and stopping many times because it's moving in steps. So it's not easy to operate this machine at extremely high speeds, because extremely high speeds needs continuous operation, not operating at steps. So for very high speeds, we prefer to operate other kind of machines based on working in the mode of weakening or field weakening at high speeds. However, stepper motor is not preferred at this weakening or high speeds. Right. So as you can see, we have 8 main advantages and only 2 drawbacks. So this motor as a total is good. Right. What are the types of stepper motors? We have 3 different types of this motor. We have one type is called the active rotor, and this active rotor means the rotor itself is based on permanent magnets, so it's active. The other type is reactive rotor, where the rotor is based on variable reluctance, so the rotor is just iron, no permanent magnets in the rotor circuit. And a combination between active and reactive rotors, or variable reluctance and permanent magnet motors, which is hybrid stepper motor. So we have 3 main types of these motors: variable reluctance, permanent magnet, and hybrid type. Right. What are the applications of stepper motors? Applications like printers, like graph plotters, like tape drivers, like disk drivers of computers, like machine tools, like XY recorders, like robotics, like electric watches. So these are the main applications of the stepper motors. Let's start with the first type of the motors, which is a variable reluctance one. As we described variable reluctance, it means we have no magnets. All of the motor are based on iron, no any magnets used in the rotor circuit. So the construction, we have stator, and we will call here the stator poles or teeth. We have teeth in the stator, as you can see. This configuration, we have 4 teeth, and this one we have 6 teeth in the stator. So the stator is composed of some teeth, as you can see, and these teeth or poles can be connected in such a way to many coils in order to energize this motor. For instance, we used here for the 4 teeth, we used 2 coils, coil 1 for these 2 teeth, and coil 2 for the other 2 teeth. This is for the stator. For the rotor, as you can see, it's just a bar of steel or iron, okay? And it's composed here of 2 teeth. Here we have variable reluctance rotor with 4 teeth. So there is no definite configuration for variable reluctance. We can design the variable reluctance stepper motor by any shape and any number of teeth based on the required operation, as we are going to describe. So there are some relations we are going to use in order to design our motor, in order to operate this motor at a certain step angle. We are going to say if the motor moves a part of angle, we will call it as step angle. So based on the required step angle, we are going to design our motor. This is an example here for a construction of 6 stator teeth and 4 rotor teeth. What's the relation between the stator teeth and rotor teeth and the angle of the step? Simply, this is a relation: theta, which is the step angle, equal to 360, which is 1 complete revolution, multiplied by ns minus nr, divide ns nr, where ns means the number of stator teeth and nr is the number of rotor teeth. So based on the required angle, we need to design our teeth or our motor. Simply, for this configuration, we have 6 stator teeth and 4 rotor teeth. So as you can see, the relation here, theta f equal 360 multiplied by 6 minus 4 divided by 6 multiplied by 4. So we have step angle of 30 degrees. How can we energize this motor? Simply by this sequence, we will have a truth table, okay? And with a sequence of pulses, we are going to control this kind of motor, and we are going to describe in details how we can apply these pulses as a sequence of pulses and how the motor is going to move. And finally, we will say how to make this power circuit to control the variable reluctance motor. So simply, let's start with the operation of the machine in one of the modes, which is called full step operation. So simply, this is our motor. Here we have 6 stator teeth and 4 rotor teeth, and we are going to describe something called the full step operation. This is one of the control steps or control techniques used for stepper machines. In order to understand or recognize the operation of any stepper motor, we need to agree together with some rules. First, we will assume a random position for the machine before applying any pulses to the machine. And when we apply the first pulse, we will assume that this is the first operation, because it will depend on the machine position before of this step. So if we applied the first step, the motor will operate in a certain position like that. In order to apply second step, we have to go to first step in order to recognize the previous operation, the previous position. And based on the previous position, we can change the sequence of pulses in order to move the machine in certain step. So this is the idea of the operation. Fine. But what is the rule of applying?
Victor,
Fadal.
can you repeat the last point again?
Again. In order to recognize the operation of the motor, we will apply some steps. Like you can see here in the table, we have, for instance, 12 steps. First step, we will assume that before this step, the motor was randomly has near position to that step. So when we apply the first step, it will be in that shape. Okay? And we will describe how it is became in this position now. In order to apply second step, you cannot apply second step without looking for the first step to see the position of the motor, in order to apply the next step and apply and recognize the motion of the machine. Right. So a question for you, Shabab. If we applied a flux based on the energizing coils of these 2 teeth of coil number 1, and we can assume that the rotor is يعني ايه far from this position, but it's not very far, يعني say for 10 degrees for instance, okay? And when we energize this coil, the flux will start moving from the top to bottom. Assume this one is N and the bottom is S. So the flux is going to move from up to down. So the flux lines has two criteria we have to recognize. First, flux lines prefers to move in iron instead of air because all of time the small reluctance will be preferred for the flux lines. صح يا شباب؟ The reluctance of air will be very high compared to the reluctance of the iron. So the flux lines will prefer to move in iron instead of air. So if we assume that in the beginning we have the first position like that, يعني assume this is the position of the step, not in the as it is drawn here. So the flux will prefer to move like that here and return to the other teeth. Is it right? Okay, شباب?
Yes.
Right. Okay. So this is the first criteria for the flux lines. Second criteria, all of time flux lines prefer to short its path. So it's elastic wire. It will try to make the path very short. So it will move the rotor in that direction in order to make the flux lines, in order to make the flux lines moving in a straight line like that. So in order to move flux line like that from up to down, it will make the flux line to be short as possible. Okay, شباب? So for the first position, assume we operate the motor when we energize coil number 1, and this is now the position of the machine. We can remove these lines now, and if you didn't recognize the operation for the first step, you will understand it inshallah for the next step here. Time. So assume now this is based on the first energization due to energizing coil number 1. So we will assume all of time that this is the reference. This is the first position of the machine. When we apply the pulses or energize coil number 2 instead of coil number 1, which means here coil number 1 is 0, which means not energized. Coil number 2, in step number 1, 2, and 3 were not energized. Here in step 2, we will energize coil number 2 and leave coil number 3. Let's see what will happen. Again, in order to understand what will happen in this step, we have to look on the previous step. So look at here. If we energize coil number 2 here, so this means this will be N for instant, and this will be S. So the flux lines prefer to move in this direction. Type. Now, what is the distance between pull in and this teeth and that teeth of the rotor? Hey, شباب. Can you imagine what is the angle now? Simply, we have 90 degrees between the two teeth of the rotor. Is it right?
Yes.
تمام.
45.
لا مش 45. How it comes 45?
Between the stator winding and the
Doctor, I think it's 60 from the top teeth and 30 from the left teeth.
Right, let's make it in angles like that. يعني now, if this is our configuration, now this angle is 90 degrees. And from
Okay.
here, sorry, to the center here, it's not easy to يعني from that place, let's make it with laser pointer, from that place to this place, it's 60 degrees, is it right? تمام. So this is 90 and this is 60, so the difference here will be 30 degrees.
Yes.
So which is preferred now, to attract the 30 degrees or to attract the 60 degrees, which is nearest to the pen or to the stator teeth?
30.
The 31, صح كده? So
Yes.
the flux lines now will prefer to attract these teeth and continue moving like that until reaching to S. And then it will rotate the machine in order to make the flux line very short. So it will be in that position. So for now, when we applied the energy, or energized coil number 2, the machine moves 30 degrees from the reference. Is it right?
Yes.
So this is the position based on this sequence of pulses. So when we energized coil number 2, the machine rotates by 30 degrees and it stopped at the position of 30 degrees. Any question regarding this step, Shabab? Anyone need to repeat this step? Okay, okay, good. Right. So now when we change the pulse from 1 to 2, now we are going to change the pulse to coil number 3 and see what will happen. So for step number 3, we will energize coil number 3, and in order to recognize how we can find the position at step number 3, we have to look for the machine configuration at step number 2. So from here, now we are going to energize coil number 3. And if we energize coil number 3, we will find that the flux will prefer to move through this tooth, تمام يا شباب, and moving like that up till return back to tooth number 3. Is it right? So if this is the case, the machine will move another 30 degrees and will be in that position. So here we have the new position, which is 60 degrees. So this is the pulse or the sequence and the position for step number 3. In order to recognize the motion for step number 4, we have to get it from position number 3 again. So for number 4, we are going to start repeating the sequence. We will start again from coil number 1. So we will de-energize coil number 3 and start energizing coil number 1. And as you can see, coil number 1 is 30 degrees apart with this tooth. So it will attract this tooth and move the machine by 30 degrees to be in this position. Is it clear, Shabab?
Yes.
But I have one question.
Yes, well.
If we didn't energize the next coil, the machine will stop instantaneously?
Exactly.
Oh.
Not instantaneously. Again, this is a very important question.
Mhm.
Based on our discussion in the beginning, we said that the operation of this motor is based on to be in standstill. So this means if I apply the pulse sequence of S1, the motor will stay at this position. It will not move. Only the machine will move if we change the sequence of pulses.
Yes.
So motion here will come due to the change of the sequence of pulses. Okay? And during the standstill, because we have flux which is moving, in this case here, for instance, we have flux lines moving here. So if you applied a load to this shaft, it will be captured by the flux. The motor will not move. And this is the idea of the stepper machine. Okay, Shabab? Is it clear?
Yes.
So the motor can move only when we change the sequence of pulses. And if you apply certain pulse for a long time, or keep it for a certain pulse like that, the motor will stop at this position. Okay, Shabab?
Okay.
Right. So what will happen after these 90 degrees? We are going to continue the sequence of pulses by the same way, 1, 2, 3, 1, 2, 3, 1, 2, 3, up till moving for one complete cycle of 360 degrees. So this is one complete cycle operation for a variable reluctance using something called the full step operation. Why it's a full step operation? If you apply the relation, what we already calculated in the previous slide, here, as you can see, when we apply the relation based on 6 stator teeth and 4 rotor teeth, we got the angle or the step angle of 30 degrees. So this is called full step because the motor moves with 30 degrees. If the motor moves with different degrees, we will call it with another name. But for now, 30 degrees means this motor is moving with full step. Let's describe something else called half step operation. What's the meaning of half step operation? Let's compare between position number 1 and 3 here, and with the full step operation, positions number 1 and 2. Yani if you can find here position number 1, coil 1 energized, and 2, 3 are de-energized. And the motor stopped at reference 0. For step number 3 here, coil number 2 is energized and other coils are de-energized, which is the same like step number 2 in the full step operation. Is it right, Shabab?
Yes.
So the first step here is the same like the first step in the full step operation, and the third step here, or third position, is the same like second step in the full step operation. Right. So we have here 0 angle and 30 degrees. We need to move the motor in between these steps. So instead of have 0 then 30, we need to stop the motor at 15 degrees. How we can do that? And this is called half step operation. In order to make half step operation, simply we are going to make OR gate for the pulses of the two cases, 1 and 3. So as you can see, here coil 1 is energized, we will keep coil 1. Here coil 2 is energized, so we will keep also coil number 2 energized. Right. What is the principle for this kind of operation? Let's start from the beginning. At position number 1, we agreed together that if we energize coil number 1, this will be the position of the rotor. Now, if you applied a signal to coil number 2, while coil number 1 will be energized at the same time. This means you have some flux lines moving here in that direction, and you will have some flux lines moving from this tooth through this tooth or teeth of rotor and return back to coil number 2. Right. For now, we have two different flux lines. One would like to keep the rotor in the same position, and the other one need to make its path very short in order to reduce the length of the flux lines. What will happen? Now, the two flux lines will fight together until making the motor in equal distance between each other. So, if the motor moves only for 15 degrees, as you can see, for flux lines coming from tooth number 1, it's shifted from the rotor tooth by 15 degrees. And here also for coil number 2, it's shifted by 15 degrees from the other side. So now the rotor is in equilibrium. So this will be the half-step operation. So this is the principle of the half-step operation, شباب. If we apply the pulses between steps 1 and 3 to be OR gate between both of pulses, which means energize coil number 1 and energize 1 and 2 together, and then only energize number 2. This will move the machine from position 0 to 15 degrees and then to 30 degrees, and so on by the same way. So the sequence of pulses now will be applied like that. Coil number 1, 1 and 2, 2, 2 and 3, 3, 3 and 1, and so on. So for this case, the step angle is 15 degrees, which is 1/2 of the full step angle, and the number of pulses for one revolution increased to 24. How we can get this number? Simply by dividing 360 to the step angle. So 360 divided by 15 will give you the number of pulses per revolution, which is 24 pulse in this case. Any question, شباب? This, تفضل.
Is it safe to assume that the torque is doubled since we are using two coils instead of one?
Yes, we are going to describe this now in details. We are going to describe what will happen to the torque now. Right. So as a summary for the half-step operation, we operate the machine as coil number 1, coil 1 and 2 together, and then coil 2, and so on. This make half-step operation. Type. In order to reverse the machine direction, for the full step operation, can we return back to the full step operation here? Now we apply the supply to 1, then 2, then 3, and if we move the supply in this direction, I mean energizing coil in this sequence 1, 2, 3, the machine will move in the other direction. Is it right? If you would like to reverse the direction of the operation, simply instead of making the sequence 1, 2, 3, keep the sequence 1, 3, 2, and the machine will rotate in the reverse direction. So this is a way how we can reverse the machine direction, simply by reversing the sequence of pulses. So instead of supplying 1, 2, and 3, no, it's supply 1, 3, and 2, and so on. So this will make the operation or the motor direction reversed. Right. The second note, for full step operation, we energize only one coil each step. But for half step operation, we need to energize one coil, then two coils together, then one coil, and so on. So this is the sequence of the half step operation. The half step angle equal to full step angle divided by 2. And the number of pulses per revolution equal to 360 divided by step angle. What is the drawback of half step operation? For half step operation, شباب, we have pulsating torque. Why it's pulsating torque? Because as we described, we energize one coil, so we will have certain torque. If we energize two coils, we will have higher torque. And return back again to one coil, so the torque will be reduced again. So in this mode of operation, we have a problem of the pulsating torque. Okay, شباب? So this is one of the drawbacks of the half-step operation. Right. What is the motor speed? How we can calculate the motor speed? Simply, motor speed will be 60 multiplied by the frequency or of the applied pulses divided by the number of steps. So this is the machine speed in RPM, where F is the number of pulses per second, which represents the frequency of the pulses. Right. The drawbacks of variable reluctance type is the smaller torque compared to other types of permanent magnet and hybrid. Why it's lower torque, يا شباب? Because we don't have any permanent magnets in the machine. And simply, if we return back again to any shape, if we applied flux or energize coil number 1, this means if the upper tooth is N, the lower tooth will be S. This means the flux lines will move from this part to that part. So the distance now between the N and S pole is greater than the one in permanent magnet. Yani, as you can see, this is now the distance. So the distance between the two poles is almost the diameter of the stator. However, if you make permanent magnet motor, which means you will have poles here in this portion of rotor, so the flux line will be very short. And from the criteria of flux lines, if the flux line became shorter, it will be much stronger. And this can work with higher torque. Is it clear, شباب?
Yes, clear.
Okay. So the drawback of variable reluctance is that it's smaller torque compared to permanent magnet type. Also, the typical step for variable reluctance in industry are like 1.8, 5, 7.5, and so on. These are the typical steps used in industry. However, there is another technique for step operation or control of stepper motor called microstep. In microstep, we can move the machine in very, very small step, say 0.1 degree. But it's not possible to apply this kind of control technique with variable reluctance because we need very high number of switching, teeth in stator and rotor, and this is not easily be made in variable reluctance motor. However, it exists a lot in hybrid motors. Okay, شباب? Okay. Now, what is the power circuit that we can apply or use in order to make this kind of control? Simply, as we described in the beginning, we have many configurations. Configuration of variable reluctance is not fixed. We can design our motor based on our requirements, based on the required step angle, okay? And then we can design our motor as how many teeth in stator, how many teeth in the rotor, and so on. For instance, here, if we have 8 stator teeth and we can apply 4 coils, so 4 coils, we can say this machine is 4-phase because each 2 teeth will be wounded with 1 coil in order to make 2 poles N and S. So simply, we will have the coil like that, and if we need to energize this coil, we will connect this coil in series with power electronic switch and between 2 terminals of DC supply, 0 volt and VCC. And if we apply a pulse to this transistor, it will energize this coil. And in this case, the machine will operate based on energizing coil A. If we need to make energizing for other coils, it will be made in the same way. So for the construction of 4 phases, we need 4 switches and DC power supply in order to make this control. The advantage here in this circuit, شباب, as you can see, all of transistors are common emitter. Here, this is the emitter for all of switches, which means all of these transistors can be energized or controlled using the same supply. And this is very important. We don't need to make any isolation here for this kind of drive circuits. Type. So this is simply the power circuit needed for variable reluctance stepper motor. If we compare now between different machine torques according to the operation, assume we have stator of 1, 2, 3, 4, 5, 6. So this is 12 teeth, 12 stator teeth, and we have 1, 2, 3, 4, so 8 rotor teeth. If we apply the full step operation for this kind of motor, we will find that the step angle is 15 degrees. So we connected here the machine, as can be seen here. The 4 stator teeth are connected to one phase. So coil A is wounded on 4 of the stator teeth. So we have here 3 phases. Is it right? Phase A, B, and C. So comparing this to another shape, if we used only the same construction, 12 teeth, and the angle is 15 degrees. However, we used 4 switches instead of 3 switches. So we are going to make it here as 4 phases. So it can deliver higher power because we have 4 phases now. Okay, شباب? So if we increase the number of phases of the machine, it will increase the machine power and the machine torque as well. Right. Comparing this to the third technique here, it's 4 phase also, with the same number of stator and rotor teeth, and the step angle is 15. 4 switches are required, can deliver higher power compared to the same number of phases because of half-step operation. If we operate the machine in half-step operation, which means coil A and B are energized together at one of the machine modes or one of the machine steps, it will deliver higher power. Okay, شباب? So the torque can be increased in many ways. So in this machine, it's very easy to change the machine rating with the same construction based on what is the method that you are going to control. Are you going to make full step operation or half step operation, or you are going to make the phases 3 phase, 4 phase, or more than that? Okay, شباب? So this design is very flexible, and you can attain any required power and torque. Based on our discussion, this is the homework number 5 for stepper motor. We need to design a variable reluctance stepper motor that can move with a full step of 2.5 degrees. The required, what is the motor speed? Is the number of pulses. Frequency is 5 kilohertz. Propose a power circuit for your design. So you have to design your own circuit. I mean, what is the number of phases? What is the shape of the circuit? So this is the design required. Draw the machine section showing the operation for 2 successive steps. So the cross section we have drawn here or discussed here in this class. We need you to make 2 successive steps. Say, for instance, step number 1 and step number 2. We need you to draw the cross section of the machine, showing the rotor position and stator teeth and the energized coils in the same way like we made here in this class, and write down the lookup table for the sequence of pulses. So this is the homework for the stepper machine part. Any questions, Shabab, regarding this homework?
When the submission of the homework, Doctor?
We are going to finalize the stepper motor by the end of this week. So next week at Monday. Okay. Is it good for you, Shabab, or not?
Make it until Wednesday, Doctor, because the major will be, I think, on Sunday.
You have majors. Okay, no problem. So Wednesday next week, I will send you on Blackboard.
Doctor, regarding the
Okay.
major, I think we postpone it to week 14, right?
What is your opinion, to be in week 14 or week 15? We need to discuss. But let's finalize the recording now. Okay, and yeah, okay.